This is the Chapter 5 homework number 2 video. The hotly anticipated sequel to the Chapter 5 homework number 1 video, which is available in stores now. So we're going to start with number 49, which means I need to make my book appear here. Okay, so here's my book. I did that. I didn't do any tricks this time. I'm just going to put the book here because you guys don't fall for these things anyway. You guys are probably out shooting all kinds of TikTok content. You already know all the little tricks. Okay, let's figure out which species are chiral and which ones are not chiral. So on A, we have this carbon in the center, right, of this plus sign, and then we have 4 different things attached to it. So 1, 2, 3, 4. Those are all unique groups. So that one's definitely chiral. Okay, B. Here's a chiral carbon. Here is a chiral carbon because these 2 groups on the ends of the molecule are not the same. And here's another chiral carbon. Okay, so since I don't have any symmetry in this molecule, this would also be chiral, right? It has 3 chiral centers. And if you have at least 1 chiral center and no plane of symmetry, then you are a chiral molecule. Okay, so what does a plane of symmetry look like? Question C has a plane of symmetry, because the key is this group at the top is the same as this group at the bottom. So there's a plane of symmetry that runs straight through this center chiral carbon. Okay, so we actually have 3 chiral centers, but an achiral molecule overall, which I think somebody asked about a situation like this in class. Okay, so this is exactly what we're talking about. When your plane of symmetry goes through the chiral center, sometimes you can have an odd number of chiral centers and an achiral molecule. So this is also a meso compound. And then this guy, so this group and this group are the same. So we have to be on the eye, keep an eye out for symmetry. We have 3 chiral carbons. We don't have a plane of symmetry anymore though, because this OH is on the wrong side down here, right? So it's not reflected across my paperclip in the same way that this one is. If I were to just look at one half of the molecule kind of lining up or reflecting with the other half. So this one's symmetrical, this one's not. So D would be chiral. Okay, I need to go back to my paper now, so give me a sec. Okay, 51, we're converting Fisher projections into zigzags. So let me write all these out and not on camera. Give me a sec. Okay, we're back. I got them all drawn for 51. 51. Okay, so we got to convert this to a line angle drawing. So first I need to get my CH2OH written down. So here's my OH. This is going to be my CH2. And then I'll have 1, 2, 3, 4, 5 carbons. So 1, 2, 3, 4, 5 carbons. CO2H tells me this is a carboxylic acid. So there's my molecule. And now I need to figure out where do all of these groups go. So if I want to use my floating man perspective, remember your head needs to line up with the head of the Fisher projection. So here's my man above, and here's my man below. Okay, they both have to line up with, the head has to line up with the head, and the feet have to line up with the feet. Okay, now it's a matter of which perspective do I want to do first. I'll do my floating above perspective first. So I'm looking down onto this carbon, okay, which is carbon 2. So 1, 2, did I lose a carbon? What happened? Did I draw an extra one? No, I'm good. This one's not chiral, so I'm going to call this carbon 1, this carbon 2, and this carbon 3. See, I almost made a mistake there. It's easy to do these things. Okay, so I'm just going to number my chiral carbons, and if it's easier, you can number the whole chain. Just make sure you number the whole chain here. So this is carbon number 1. And if I'm looking at it from floating above, my right arm is going to be going into the page. My left arm is going to be coming out of the page towards me. Okay, so what's on my left then from this perspective? On my left is this OH. So this one's coming out of the page. Okay, then carbon 3, this OH is also on that same side. So I don't even have to reimagine my perspective if I don't want to. I could just say, well, since these are both up carbons that I can look at from above, they're both on the same side of the Fisher projection, they'll be on the same side of my line wedge dash. That just leaves carbon 2. So carbon 2, let me redraw down here. So I need to look up at carbon 2 so I can figure out what is going in each direction. So now my left hand is going to be going into the page and my right hand is going to come out of the page. You can always remember it's the opposite of the floating above perspective. The floating underneath, okay, left hand's going into the page, right hand's coming out. So since this is on the left, wait, I'm looking at carbon 2. Since this is on the right, okay, it's going to be coming out of the page at me when I'm looking at it from underneath. So that would be on the right. Okay. If you rotate this entire structure, a lot of people drew it with this OH pointing down and this carbonyl pointing up. That's going to invert all, and not invert the stereochemistry, but these are all going to be written as dashes because basically you took the molecule and flipped it 180 degrees. Okay, but that would be fine. And if you're not convinced that that would be fine, go through, try to assign R or S. You'll see you get the same designations either way. All right, B, I have a methyl and then a chiral carbon. And I have 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5. This last one is attached to an OH, so I'll put that in my zigzag. And then this is my methyl. So these are my chirals, 1, 2, and 3. 2 and 3. Okay. So let's do the man underneath this time, since we have 2 carbons that he can look at. All right. On my left, I have this one on my left. Okay, if I'm looking at this from underneath, if it's on my left, it needs to be going into the page, like my left arm would be if I was laying in the page like this. Carbon 3, right, these are the same. Okay, the OHs are on the same side. And since carbon 1 and carbon 3 are both down carbons, I can just say this is going to be an OH, and then my methyl must be coming out. All right. Then carbon 2, I can look at it from above if I wanted to, or I could say, well, I know this is an up carbon and these are down carbons. So if this is on the right, okay, and this group is also on the right, when I'm on an up carbon, this one's going to be the opposite of whatever this was. If that was really confusing what I just said, you can just look at it from above with your man in the paper. The man in the paper says, this thing's on my right, and my right arm is going into the page, so this chlorine must be going into the page. And that matches what I said a second ago. These are both on the right of the Fisher projection, okay? So when we draw the zigzag, if the CH3 is coming out at you, the Cl must be going back into the page, okay? Because the up carbons, this perspective and this perspective are going to be opposite as it relates to the Fisher projection. So it's just a little shortcut, but it may be too confusing to do it that way. Okay, C, I have my aldehyde. I have my aldehyde, and then I have a chiral carbon, another chiral carbon, and then an achiral carbon with an OH on it. So chiral carbon 1, chiral carbon 2. Okay, so carbon 1 I have to look at from underneath. So this OH is on the right. My right hand is coming out of the page, so this must be coming out of the page as well. Carbon number 2, I have to look at from above, or I can just say it's going to be the opposite of whatever this was. If this was out of the page, this one has to be into the page since they're both on the right. But just to prove that to ourselves, let's look at it. This is on the right, and my right hand is going into the page when I float above the paper. So this must be going back. Okay, so really you can use the floating man, or you can just figure out one of these orientations and then say, okay, if this is an odd number carbon and this OH is coming out of the page, then all my odd numbered carbons, whatever's on the right, is coming out of the page, and all my even numbered carbons, whatever's on the right, is going into the page. Again, don't do that if it's confusing. Do it the whole way the other way if we like that better. Okay, one more. So I have a cyano. I'm going to actually draw this out as N triple bond C linear to this chiral carbon, and I have 1, 2, 3, 4 of those. 1, 2, 3, 4, plus my CH2 that has the Cl attached to it. So 1, 2, 3, 4 are my chiral centers. Okay, so let's go above this time. So looking at carbon number 2, right? My left hand is coming out of the page. Carbon number 2, this OH is going in, is on the right. Okay, my right hand is what's going into the page, so this one must be going back into the page. Carbon 3, so let's do this the shortcut way. Carbon 1 and carbon 3, or I'm sorry, carbon 2 and carbon 4, right? I started with carbon 2. Carbon 2 and carbon 4 are both up carbons. So if this OH is going back when it's on the right, then this OH must be coming forward when it's on the left. Okay. And then for carbon 1, I can just compare that to carbon 2. These are both on the right, but carbon 1 is a down carbon, so it's going to be the opposite of carbon 2. Okay, so that means this one must be coming out of the page, since carbon 2, the OH on the right, was going into the page. That's the whole reason why we have to flip our perspective from above or below, is because it matters if you're on an up carbon versus a down carbon, the Fisher representation is going to change. Okay. And then I can do the same thing on carbon 3. I can say, well, this OH is on the left on a down carbon. On an up carbon, an OH on the left came out of the page. So on a down carbon, this must be the opposite. It must go into the page. Okay. So again, you can always use the floating perspective if that makes more sense to you. But personally, I like to just use it the one time and then base all my other configurations off of that one carbon. Okay. 52 is the next one. Okay, you guys wouldn't know it, but I was actually just gone for like an hour talking to people in office hours because I love when people come by in office hours. And I also like the Office Hours Live podcast with Tim Heidecker. Pretty funny podcast if you like Tim and Eric, if you're into that kind of weird stuff. So anyway, let's talk about this next question. So we want to know our Fisher projection of this guy. So let me set it up first. I have C double bond O with an H, and really I guess I don't need to draw that C. Let me start this over. So C double bond O with an H, an aldehyde, and then I have 3 chiral centers, and then alcohol at the over. Whoop. Oh, you guys can't even see this. Let's move it over here. Okay, so this is what I have, right? I have my CH2OH, my A chiral carbon down here. I have my aldehyde, and I have 3 chiral centers, 1, 2, 3 between it. So 1, 2, 3, 1, 2, 3. Okay, so what goes where? Well, what goes where? Well, we need to enter the paper first. So let's go from the bottom to do carbon 1. If I put my man underneath, on the right side, right, my arm is coming out, my right arm's coming out of the page from looking at this from underneath. I line my head up with the head of the molecule. I get my OH on the right, which means my phenyl must be on the left. Okay, and if my phenyl is on the left here, that means this OH on carbon 3 is also on the left since it's going the same way as the phenyl. And then on carbon 2, I need to float above to look at that one. Okay, my left arm is the one coming out of the page when I'm floating above, so this would also go on the left. Okay, so there's A. Let's do B now. So for B, I'll put my alcohol at the top, and then I have 2 chiral carbons, 1 and 2, and then I just have my C triple bond N at the bottom. Okay, so looking at this carbon from underneath, this would be coming out of the page, which would be my right hand. Okay, and this is carbon number 1. Carbon number 2 should be the opposite. Okay, but if I look at it from above just to make sure, now that coming out of the page would be my left hand if I'm floating from above and looking down, so this would be over here. I need to fill in my H's. All right, and then C, I'm going to do C the expressway. All right, you guys all right with that? You can't tell me no because this is a video, so I'm going to do it this way if I feel like it. 1, 2, 3, 4 chiral carbons, right? 1, 2, 3, 4 chiral carbons and a CH2OH. We're going to do it the express way. We're going to just assign this carbon and we're going to base everything off of him. So looking at this from underneath, this OH would have to be on my right. okay, for carbon 1. OH on the right for carbon 1. Okay, then carbon 3, these are both down carbons, so if this one's on the right, you guys can't even see this shit. God damn it. Let me start my explanation over. Pardon my French there. Okay. If I look at this from underneath, right, this OH is going to be on my right hand, so that goes on the right side. Then this one is one I would also look at from underneath. So carbon 3, since this is the opposite, this is a wedge and this is a dash, this one has to be the opposite side then. So this would go over here. Then carbon 2, remember the up carbons have the opposite Fisher projection drawing from the down carbons. So on this one, I have an OH coming towards me. This one's going back. That's the opposite. So that's actually going to be on the same side of that Fisher projection. Okay. And then I know that this chlorine is the same as what's on carbon 2, so I can put my chlorine over here. Now, again, you can always just use the floating perspective to draw in every single center, but once you start getting more comfortable with it, you can also kind of just do this. Assign 1, go through all the carbons on that same, pointing in that same direction, and assign off of what you did on this first one, and then flip that to do the top carbons. Hopefully that makes at least a little bit of sense. Okay, time to turn this back into the book. So here we go. Boom, we're back. Again, I also changed my pen into a paperclip. So, because paperclip is a good pointer. So we're doing 73. Try to get my camera to not fall over. You guys remember this from 241? Stupid camera is always falling apart. It's not any better. If anything, it's in worse shape now. Okay, we want to know, are these same, constitutional, enantiomers, diastereomers, conformers, or different molecules? This one, the key for this is thinking about those operations that we talked about in the group exercise, the in-class exercise on September. Excuse me, on September what day was that? Last Friday, the 24th, the 24th. Is that really when we did that? Yeah, the 24th. We talked about those operations that with the in-class exercise on Fisher projections, where we looked at what happens if I rotate this by 90 degrees, what happens if I swap two groups, what happens if I rotate this whole thing 180 degrees. That's what I'm mostly going to refer to make these assignments. So comparing this one with this one, what did we do? Well, the CH3 is in the same place, but none of the other groups are in the same places. They've all moved around. So really what I'm doing is fixing this CH3 in place, and I rotated these groups the same direction. So the Cl came over to where the OH was, the OH moved to where the H was, and the H moved down here. So that's really the same thing as just rotating about this carbon-carbon bond. And we said when we do that, if we fix one group in space and we rotate the rest, that does not change our conformation. So these two are the same. These are the same molecule. Here what happened, well, the Cl and the OH swapped, right? They're on opposite sides. And the H and the CH3 swapped as well. So we can think about this as our swap two groups, then swap two groups again rule, right? I made one swap, this one and this one swapped, and I made a second swap. So that one swap inverts the stereochemistry, a second swap returns it back to the original because you basically inverted it twice. It's like a double negative. Other way of thinking about this is I pretty much just took this entire Fisher projection and rotated it 180 degrees. So the CH3 is at the top, the OH goes over to the right side, the Cl goes to the left, H goes to the bottom. Okay, both of those operations do not change the structure. They don't change any of my chiral centers. So these are also the same in B. In C, what happened in C? For C, what did happen in C? In C, this looks like I rotated this by 90 degrees, right? Because this came up, this went up here, this H came down here, the Cl came down here. When you rotate it by 90 degrees, you get an inversion of the stereochemistry at this carbon. So this carbon is going to have the opposite configuration of this one because that 90-degree rotation changes. Remember, these going up and down bonds are going away from you, and side to side, the horizontal bonds are coming towards you. I've switched now what's going away versus what's coming towards me when I rotate by 90 degrees. So that is not the same molecule anymore. Okay, this would be a pair of enantiomers because we have one chiral center that has inverted its stereochemistry. D, what did I do on D? I kept my H and my CH3 in the same places, but my OH and my Cl swapped. So I swapped two groups. Remember, swapping two groups inverts your stereochemistry. So since I only have one chiral carbon that got inverted, these would be enantiomers. Remember, for enantiomers, we invert every chiral center. For diastereomers, we invert at least one, but not all of the stereocenters. Okay, let's look at E. You got to be careful on E. Once again, let's check these groups. This group at the top is the same. This group at the bottom is the same on each of them. So every single chiral carbon just had its H and its OH swap positions, but the rest of the groups, the vertical groups, didn't swap positions. So these are all like a swap two groups operation at every carbon. So this one got inverted, this one got inverted, and this one got inverted. We inverted all of our stereocenters. These are enantiomers. Another way of looking at it is if you just put a mirror in between them, you would see that one is the mirror image of the other, so they must both be enantiomers. Okay, number F. On number F, again, we have the same thing on the top and bottom, so that checks out. Here I have a group that's not swapped, so these two carbons are the same stereochemistry. These two carbons are inverted from each other, right? I swapped my H and my OH, so I inverted this chiral center. So these are not the same, and these are the same. So I inverted one, but not all of my chiral centers, and that happens when we have, that's how we get a diastereomer. These two are diastereomers. Enantiomer, you invert all of them. Diastereomer, you only invert one, at least one, but not all of them. Okay, number G. Let's look at number G. Number G. We got to be careful on number G because this group is now the same as what's at the bottom of this structure. And this group is the same as at the top of this structure. So to really compare these, I need to take this guy and do a 180-degree flip to put this CO2H at the top and this CH2OH at the bottom. And when I do that flip, this OH then would move over to be the right on the bottom carbon. So that checks out. This one would move over and now be on the left. So that is also the same. And then this bottom one, when I rotate it, this OH is going to come over to be on the right of the top. So that checks out. So G, these are actually the same. These two molecules are the same. Okay, last one, the really tricky one. Top and bottom groups are the same, right? These definitely look like mirror images of each other. So you might want to say they're enantiomers. If you look at the stereochemistry, this one got inverted, this one got inverted, this one got inverted. But because these top and bottom groups are the same, I could just take this whole thing and flip it 180 like I talked about on the last problem. When you flip a Fisher projection 180 degrees, you do not change the stereochemistry of anything. So it's always valid to rotate a Fisher projection by 180 degrees if it makes comparison easier. Okay, so if I flip this, then I'll see, okay, this OH is going to end up on the left on top. This one's going to end up on the left on the bottom. This one's going to end up on the right in the middle. So these are actually the same molecule because there is a plane of symmetry through each of these molecules right down that central chiral carbon, or the central stereogenic carbon. It's not actually chiral in this case. Okay, it's not, the overall molecule is not chiral is what I mean to say. Okay, because each of these are two meso compounds. This is a meso compound. This is the mirror image of a meso compound, which the mirror image of a meso compound is the same as the original compound. So they are not enantiomers of the same compound. Okay, this concludes this video key. I hope this was helpful. And if not, please email me and ask me a question.